when I mentioned the partitioning, I mentioned that we decompose the domain so that each CPU has an equal number of agents. Actually, that is not true, because agents are heterogeneous. If it's a car, it takes a different time for computation compared to a pedestrian. If this car is at a junction, it takes longer time. And if I force the agents to work, pedestrian to work along the side of the road, it takes longer time to compute. So agents are highly heterogeneous. If I assign the same number of agents to each CPU, depending on what they are doing, in some CPUs it takes longer time, in others it takes shorter time. There's load imbalance. To address that, so this time analysis shows how long it takes to, if I use assign equal number of agents to each CPU. The head of this blue is the end of the computation. As you can see, this rank finishes its work quite early, but this one takes quite a longer. The difference is almost 900 seconds wait. That's a huge waste of computation resources. So instead of doing that, what we did is instead of assigning equal number of agents, what we did is we measured how long we measured their execution time, and then we used this execution time to partition. We partition such that summation of a partition, execution time of the agents in a partition will be nearly equal. And with that, we could reduce this 900 seconds to 90 seconds. That's a 10 times reduction. Of course, we cannot make it 0 because we don't know what the agent would do next time. And that's about distributed parallel computing, MPI. And next, since most of the modern CPUs are shared memory, they have a large number of shared memory cores, we wanted to use OpenMP to make it accelerate. And in your lecture, you learn how to use OpenMP Pragma to make a for loop parallel. Here, there's this for loop, execute all the agents. We tried the simple Pragma OMP 4. The trouble was, it didn't produce the expected performance because these agents are highly heterogeneous and there's no way we can predict how long it will take. And then we use this new feature, came with OpenMP 4, I guess. It's called tasks. It's mainly designed for handling the dynamically changing dynamic data structures and irregular algorithm. So what happens here is we start the parallel region, and here we tell this is a single region. What comes with these two brackets is a single, that only one thread will execute. And this no wait means all the other threads will not wait and go to the next stage. And then within this single region, the thread enters there, will create series of tasks. Each task will encapsulate all the data and instruction required to execute this block. It will just create the task, and the remaining threads which went there will pick these tasks and execute one by one. And once this thread finishes creating tasks, it also will join the thread pool and execute these independent tasks. This way we could reach better performance. And this shows the scalability of shared memory parallel up to 8 threads, because at that time, here it's 4. And we could reach around 94% scalability on 8 threads. We use 8 threads here because this was done on K computer, the predecessor of the Fugaku. This is reasonably high for this class of problems. And then we did strong scalability with both OpenMP and MPI with 6 million agents. Total area is around 588 square kilometer area in 1 meter resolution with up to 2000 nodes. That means around 16,000 CPU cores, and we could reach around 83% X-chrome scalability. Since it's a highly heterogeneous and a problem of different nature, we cannot actually attain the high scalability we can attain with physics-based simulation. For this class of problem, we think this is quite a high scalability. And this graph shows how the runtime varies during a simulation. So we start with, so this is with the 128 nodes, 256 and 512. And we can see runtime nearly halves. With time, runtime increases because agents migrate, move to other CPUs, and that increases the load imbalance. Once there's a load imbalance, we repartition. That reduces the runtime, and again increases, and then we repartition. So you can see how repartitioning, dynamic load balancing really contributes to improve the performance. Okay, let's move to the hands-on. For this hands-on, I will use that problem we discussed earlier. Which one? This one. I think the problem setting is either this one or this one. And your current problem is set to use 8,000 pedestrian and 500 cars. I will show you how to change it. And we can set agents at different speeds. And the current configuration set to use only 2 nodes and 24 OpenMP threads, I guess. If we run the real problem I showed you there, it takes a bit of a long, like around 70 minutes. So that's why we are using a smaller number of agents. And first, let's submit this job, understand what's there, and submit the job. And it will take around 15 minutes to run. Within that 15 minutes, since we cannot wait 15 minutes, let's look analyze results I already obtained from a pre-run. I think this data set is already you have copied into your node PC, I guess. Then let's together analyze this and animate these agents movements. So let's go to our hands-on. Please log into your account. If you have any question, please raise your hand, then I can help you. Same information means?
Let's say the young people and...
Okay. Yes. So first let's submit, then I will show you how to change and what they really have. They have different, not same information, they have different information. First let's just submit, then I will show you where these agents, the properties are stored and how to change. Okay. And then go to your directory. This should be capital S, I'm sorry. Actually, if you look at this folder, there's a file called how to run, text file. Just open it, all these necessary commands I have written there, you can just cut and paste. Please check, I may have made typing mistake like this. So make your own directory inside your directory, make a separate directory for this exercise inside your directory and move to that directory and copy the data, this one. It's a compressed file, just execute this one, it will uncompress it. and enter this directory. All right, let's look at this file. What is there? Shown in these highlighted parts are the things you can easily change. How to change other parts I will teach you later. The whatever ignore, please ignore those parts. This shows the total number of agents to be used in this simulation, and out of that 8,000 I set to pedestrians and 500 to cars. You can change these numbers, but for this simulation, don't change it. Later, you can run it at your leisure time. And this is the time step size. The simulation will run at 0.1 second time step size, and it will run 14,000 steps. That means 1,400 seconds. And if we can save this. We can save data at each time step, but that will unnecessarily stress the file system. So and also it's unnecessary. So we tell here, save the data of agents at every 100 time steps, and save the statistics collected onto graph, like on each road link, how many pedestrians are right now, and those information at 300 time steps. And strangely, I have to set a number of MPI ranks here too, because sometimes we want to do Monte Carlo simulation. That's why. So here we set the number of MPI ranks to 4. Usually this is not necessary, but since sometimes we want to do Monte Carlo simulation, then we ask the MPI to give large number of MPI ranks, and we spawn multiple simulations simultaneously. That's why we need it. So later you can change these numbers, but for the time being, let's submit this as it is. Okay. And this is your job script. In your folder, there's this one, jobs _ evac.sh. I set it to 30 minutes. I think it takes around 15 minutes. I have set it to the small job. I think better to change it to your dedicated job for this HPC school, because this may take longer time. 2 nodes, maximum node processors per node is 2, and so altogether 2 times 2 is 4 MPI process. And since Fugaku CPU has 48, and we spawn 2 MPI jobs per core, per CPU, I set the number of threads to 24 here. I think if you are executing from your home folder, we have to include this one. If it is difficult for you to change this one, since we are not going to use this result for visualizing, you can submit this as it is. Don't need to change it. Okay, I hope all of you submitted this. So next, let's look at what things you can change so that you can later play with this software. And then let's visualize results of a pre-run. So in this one, as I showed you earlier, we can change how many agents to use, what's the simulation period, and how many MPI ranks to use. That is this file. And there's a file inside data folder, there should be H here, Kochi. This shows pedestrian positions. This file has the location of pedestrians and their properties. And this has the cars properties. And this has any roads which are restricted for pedestrians and which are restricted for cars, so that you can try different strategies. And yeah, more changes are possible, but currently we don't have such a input flexibility. We have to change it inside the code. So let's look at this one, the pedestrian positions. So in the top line, it says agents, and this is the number of agents included in this file. Even though it has 10,000, we are only executing 8,000, first 8,000. So you can change it that in that evacuation.dat, you can increase it up to maximum 10,000. And this is X and Y coordinate, considering the lower left corner is a 0, 0. And I put 0.5 so that each agent will be in the center of the cell, because each cell is 1 meter by 1 meter. And so you can actually change their location as long as they are in this white area. It's okay. You can so these are the files, input file. Here, this one, it shows the properties of the pedestrian, properties of the cars, and this is the environment. Actually, this file is a PNG file. You can open it. It will be just a figure when you open it. If you can count how many pixels in horizontal and vertical, you can change the location of agent. Of course, manually changing is difficult. We have another software to automatically do it, but I didn't include it here. And this one is the graph. And these are the road links restricted to pedestrians, road links restricted for cars, and these are the junction data which we automatically generated. And this third column in the pedestrian position is the ID of the node on the graph where these agents are going to evacuate to. You can change it. Okay. And if you later I will, when we open the data on ParaView, we can actually visualize the ID of each node. Then if you can select a node inside this green area, and these are the evacuation areas, then agents will move there. Okay. So this third, as an example, I want this particular agent to move to this node. All I have to do is change this number to 3530. Okay. And these are the average speed. Of course, there's a standard deviation, other things I didn't include here. So if you want to slow down this agent, change it to a smaller value and increase it. And we generated this data according to their age. For Japanese population, there's this speed distribution, and according to that, we set these values. And likewise, we can modify the file for cars also has the same format. You can change it. And this one is restricted links for pedestrians, and for cars the same format. First line is how many links are included here. As an example, I have in this simulation, I have blocked the link number 40065, these 3 links. And nodes are not important, but even if you don't want the certain vehicle not to pass this node, we can do that. So we can increase the number and block whatever the road you need. And there's something you have to be careful. These are bidirectional. There's one link going upward and there's another link going downward, because some roads are one directional. So when you visualize it, you will see 2 numbers overlapping, and it's carefully we have to choose which number is up direction and which number is down direction. All right, so I think you have copied a large around 2 GB file in your PC. Please uncompress it. And I think you have installed ParaView 2 in your machine. So open ParaView. Open ParaView, go to File, and choose this option, load state. In your Node PC, open ParaView, go to the file menu, choose the option load state. Yes? Yes. I think. No, not ParaView and Fugaku. Please get it to your own Node PC. Oh, I think you received the instruction earlier to install ParaView in your Node PC. Okay. Then you can follow the instruction. Everybody have ParaView open? Everybody has ParaView open? Open this file in Microsoft Paint or something, dit underbar mod.png, save it with a different name, close ParaView and restart the same process, but instead of this file, you choose your new file. Can you get it work? How many of you have still problems? You can animate now using, if you press this button, you can animate it forward, backward, or go one frame at a time, and then look at different regions and see how they move around. I think everybody got it working? So with this one, now you can see each individual's movement. But for analysis, this is troublesome. You don't want to see each individual agent, isn't it? So to analyze and see what's happening, the more statistical manner, we have another data set which we collected onto the road network. So it tells at a given time how many pedestrians are there, what's their average speed, and this information. And you can visualize it by opening another ParaView window. And if you load this state, then it will show 4 windows showing how many pedestrians and cars on different part of the road network and what are their average speed and other properties. Then looking at this one, you can see where the congestions are. Looking at this one, you can see where the congestions are. When it is happening, then block that road part to cars or something, or we can restrict this many cars only. Then see how it redistributes and improve the. That all the necessary things. I'll show you. Also, I included several Python notebooks so that you can visualize the statistics. Just run these things, and then in your Windows machine, then you can see different statistics collected. The graphs I earlier showed, you can also obtain. But you are familiar with Python, so I will not. These graphs you can visualize by analyzing that data. For that, I included just execute these Python notebooks. First change the directory path. I think it's in the second cell according to your PC's location where you copied it. Maybe C something. And after that, either you can use Jupyter Notebook, Jupyter Lab, or just pure Python. And it will create these graphs, and you can add more things and then analyze in a different way. I think we're supposed to finish at 12:30. So it is 12:30. Okay, but if you have any question, please feel free to ask.